So let's get started. I hope you have a nice break from yesterday day off, and probably we know we will lose one day next Thursday because of congregation ceremony, so we will lose one day. But the other class also lose one day, so at the end is we are on the same spot. So let us continue our journey. Last time we talked about the z-test and t-test. Okay, it's so important in case you don't fully got it. It's okay. We are going to cover it again a little bit because everything will be very similar. Actually, you will see everything will be very similar to what we are doing, and just a minor variation of what we learned. So just to quickly review, hypothesis testing is you're trying to use the data to see if the claim is correct. The claim is, in our context, is talking about the population mean is certain value, and we want to see if supported by data. And the null hypothesis is you want to test is an equality. It's called simple hypothesis. And the alternative will be the composite hypothesis, will be, in our case, will be not equal to, less than, or more than. Okay, so that's two cases. And just to remind you, application decide which to be used. Okay, I think I'm not going to go over the example again. Okay, and it's important to understand that when we do hypothesis testing, we will always make mistake. Okay, there's no way we can 100% sure. So there will be mistake, and that means that we have to design what is the level of error we're going to make, expert type 1, right? Because even it's true, by probability, it can go wrong. So we have to design a type 1 error, and we'll decide how wrong we can accept, right? And this type 1 error will determine the rejection region and the acceptance region, okay? Because it is by probability, by luck, the sample mean can be very small and can be very big, right? So it is really based on luck. We have to decide ourselves what is the acceptable level of error. And p-value will be, instead of looking at critical value, where is the region between rejection and acceptance, it's looking at, suppose we adjust this level of error, okay, and this is the smallest level that you just reject, okay? And as we said, we focus on testing the based on the sample mean, and depends on whether you know the population variance. If you know, then will be the z-test. If you don't know, then will t-test. And t-test will require you to have assumed the underlying distribution is normal. Then you can replace sigma squared by s squared. Okay. So just to quickly review the z-test. Okay. And what you do is assume the null is right, and this should be around in this region. Okay. And if the alternative is more than, that means that it's large enough, then you reject, right? And large enough, you have to decide what's large enough, because we have to accept the type 1 error. If you decide the type 1 error is alpha, then you will be C bigger than the Z alpha will be the one you will reject, right? Or the p-value is less than alpha, you reject. Just to recall this example, because I think it's good to redo this again, because otherwise, after the holiday, probably you would not easy to remember everything there. So just remind you that this X bar, right, will be a bell curve, right? That is from center limit theorem, or in this case, is assumed normal. So the sample mean is also normal. And under the null, okay, remember our idea is assume the null is true, okay? Under the null, this is 6. Okay. The question would be, we are worried about things more than 6, right? So with more than 6, we would like to see how large it is. If it's large enough, then we reject, right? So the data tell us is 7. Okay, 7. Somewhere here. The question is 7 far away from 6 such that you favor H1 over H0? Okay. And by far away enough, then of course, because even if 6 is true, it can end up with 7, right? Because based on the bell curve. So we have to decide what would be the tolerance level that the type 1 error are going to accept. Okay. So we just say this area is less than the 5%, or I look at the 5% level. Okay. If 7 is within this region or not within this region. Okay. So since we know that the sigma is 4, okay, and n is 64, okay, so the standard error, SE, right, will be 4 over root 64, which is 1/2. So that means that this is actually 2 SE. Okay, right? Because the distance is 1, and SE is half SE. And you know half SE is already far away, but 2 SE is far away. So usually it's no, but let us calculate that. What is this area, right? If 2 SE, then basically just you can rewrite this as the following, right? Because this is 2 SE, so this is 2. So we want to know this area. Okay. From number to area, right? It just Excel will tell you the area on the left hand side. So right hand side 1 minus norm as this to 1 minus because this is give you the left hand side, and this will give you 2%. That means that it's far away enough, and you can actually check. This is the p-value method, so you will reject the null. You would take this one, right? So you say it's more than 6. Okay. And alternatively, you can do the critical value method, right? And critical value method is asking what is 5% of this. Okay. And if right hand side is 5%, left hand side is 95%. So from area to the number, so we just inverse norm dot s dot invert 0.95. Okay, so this will give you 1.96, 1.64, and 2 is beyond the point of no return or critical value, 1.64. We have 2, so it's deep inside the region you reject. So that's why in this question, you would say the data would favor the H1. Okay, so you will reject. Okay, so that would be the Hubble testing. Is that clear? So I will do the t-test left-hand side to show you the case. Okay, this is the right-hand side, z-test. Okay, and if you do this is what we've shown here. If you reject on the left-hand side, then you do the same on the left-hand side. I will do the T1. I'm not going to repeat this guy. And if you have the both sides, you put alpha on the both because you don't know where to go. Okay. But let me show the T. T the same, but the case where you don't know the sigma square, you replace it by S. Then the table to check will be not the Z, but the T table. Okay. Let me do the example of the T left tail. Okay. The T left tail. So again, let's look at the example again. We know the population is normal. So we know the sample mean is already normal. Okay, that is can be derived without any issue because each sample because normal, the average is also normal. And under the hypothesis, this is 4. So we know that the mean will be 4 here. Okay, of course, this is something we have to check, but there's something we want to see. Okay. And the answer we have is we got a data actually is less than 4, right? So you'll be somewhere here. Okay. The question is 3, of course, is in favor of x1, right? The question is it 4 sufficiently less than, so 3 less than 4 enough? So that we will say it is x1 rather than x0. Because by nature, it can be 3, right? Because so it's just large enough, right? So it's large enough, the question. Okay. And large enough is asking this area. Right? Is this area smaller than 5%? Right? Of course, you can use 10%, 1%, but we use 5% as standard. So it's less than 5%. If we know the sigma, right, or sigma square, right, over root n, then that would be the standard error, right? Standard error of the mean, right? We know that, then we're done, right? Because then we can calculate the z as we do in the previous question. But the problem is we don't know sigma. So have no way to understand what's going on, right? But we know that if we replace, but if we know S, right? Then we can still do the same calculation, but look at the T n minus 1 table. Okay. So let's look at the case. 4 becomes 0 here. Okay. And 3 become what? Okay. And since we don't know this guy, we are replacing this estimator, right? Our guess will be just S over root n, right? Or this is S x bar, right? Which is 2 over square root of 16. So it's 1/2. Okay. And this distance 1 by 1/2, this is -2. Right? Because the distance 1, the standard error of mean is 1/2. So 1 over 1/2 or -1 over 1/2 is -2. So you figure out that this area using the T table, right? How can we do that? Number, area on the left, standard T table. So this T, this, -2. Then you have to input this, n is 16. So look at the 15 table. True. Okay. And the answer you get is 3%. So less than 5%. So it's far away enough. So you would again reject x now and take x1. It's sufficiently small enough smaller than 3, smaller than 4. Okay. And again, you can ask the p-value method is asking where is here such that this is 5%, right? Or here, right? This is 0.05. Again, this number, right, is from area to the horizontal axis. So it will be just T inverse left-hand side is 5%, 0.05. And input is 15, our 15 table. And end up is negative 1.753. So which is bigger than 2. So negative 2. So negative 2 is deep inside the region you reject. So again, this question you reject. Is that clear? So this algorithm, or what we will do the same. Okay. The only difference is what is the standard error. So basically, you see when you do 2 sample or whatever, it's basically how to define the standard error. Okay, that will be all the procedure the same, except the standard error. And what is the which table or T table to check. So the only changes for the rest of today will be we will do this differently for different thing, and this table to check will be different. Other than that, the rest is, except the very last test, the F test, everything we do is very similar. Okay. If there's no further question, let me do the two-tail t-test again so that you know what's going on. Okay. Is there any question? No? Okay. Is there any question? It's boring if you know very well, but if you don't know, if you do not know, then it will be somewhat slightly tricky. So let me do this, and then we'll do the proportion test, and then we'll do the 2 sample. Okay, it will be more fun because 1 sample is like it's fun only with non-regression and over. Will be used in next class, but two sample tests with something A/B test will directly use in business application all the time, right? So you compare 2 features, you want to implement the old and new, whether the new is better than the old. Okay, but this is still very useful when we talk about regression and over. This is something actually more used in advanced analysis. The A/B test is something used, but that is the best you can do, right? So let's look at the example again. So there's no different except this guy. Okay, only different is not equal to 4. So again, because normal, our sample mean is also the bell curve. Okay, and under the null, we have this 4, so it's here. Okay, and we are saying that H1 is not equal to 4, right? So that means that we're going to take, if too large or too small, you reject, right? And we decide this is alpha over 2, right? And alpha is 5%, so you put 2.5% on the both sides, right? If this is far away enough, that is the case, right? Suppose I know sigma, right? Then I would know these 2 numbers, what they are, right? Once I fix the alpha, and I know sigma and sigma over n, right? The SE, right? Then I know exactly the number I reject. And now the data we got is 3. So the question is probably, is 3 going to be here or 3 going to be here? So which is true? So that's a question, right? 4 too big or too small, you reject. The question is 3 beyond the area that you reject in the pink area, right? So that's a question. Now, as we said, we do not know the sigma. So what we can do is convert to T. Okay, the same procedure. Okay. Look at T, n minus 1. Okay, N is 16. So actually look at T15. T table, the 15 one. Okay, the T table go from 1 to infinity. Okay, but we only check the 15 one because which table to check is n minus 1. Okay, so this would be 0. What will be the 3? Okay, 3 will simply be 3 minus 4 is -1, right? Will be this minus this, and over how many SE you got? So the SE will be 2 over root 16. Again, is 1/2. Okay, so the distance is 1, and the SE is 1/2. So that is -2, right? Because it's 2 SE below the mean. So that's how the formula we get, but that's the intuitive meaning, right? Is how many SE above or below the mean. If below is negative, right? And again, the question would be, what is this area? Okay. And this area, because left-hand side and T, so it's very simple. We just T, this, -2, 15, true. And because this area is not just alpha, right? It's alpha 2. So if you compare to alpha, you multiply 2, this gives you the p-value. You compare this to 5%, right? Of course, or you compare this to 2.5% also okay. But the classical method is you multiply 2 and compare to the p-value, compare to 5%, okay? And turn out this is 6%. So turn out that this is not this case, rather this case. So you can't reject it's different from 4. Okay? So that would be the idea. So this is the p-value method. If you want to do the critical value method, will be the same, right? Looking at this area is going to be 2.5%. Okay? So what you do is T inverse 0.025, 15. Okay? And this will give you negative 2.1314. So that's why -2 is not inside this region. Okay? So you will not reject. So you will still keep your H0 having mu is equal to 4. Is that clear? So that is the, don't worry, as I said, we're keeping doing the same thing again. The only thing that little bit tricky is the two-tail or two-sided test, the p-value. You calculate, you have to multiply the area by 2. Okay? And that's the only tricky part. If this is a one-sided, it's very straightforward. Is that okay? So if there's no further question, I think we just go to the new material. Okay? This is something we covered last time. Now the new material will be something you would not be surprised to see is we want to do proportion, right? We want to see, we hypothesize the percentage, right? Say the population proportion, say how many people like statistics class, right? And A may be, my power is very low, maybe A is 0.1, right? So maybe only 10% of class would like statistics, okay? And if UN is large enough, then we said that this is a binomial related distribution, then actually can approximate by normal. Okay? And one of the key thing here to look is when this is A, the variance is known. Because the mean and variance are related in this way. Okay? We know the mean and the variance is this guy. So that has to be easy because now we know the mean, no variance, we can do the normal. So that's why proportion, you can always use the z-test. You don't rely on the t. So that because we assume this is true, the variance no, right? Because when we assume we know the population proportion, we know the variance already, okay? So that is the tricky part, okay? Or the benefit of knowing this, okay? Now let us look at this example. From now on, I focus on two-tailed test, but the one-tail will be same, okay? I'm just doing a more complicated one. The one-tail will be same. So a binary data, okay? And a random sample of 50 and sample proportion is 0.5, okay? And my null hypothesis is 40% of student like math, okay? I hate math, I guess. 40% student. Maybe 40% like statistics, that's better. And turn out that, oh, surprisingly, 50% people like it, okay? So can I say H0 is okay, or actually I would not be happy, right? Is that different? Okay. So let's look at the question again. So this sample proportion, right? Follow normal because proportion data, when n is large enough, is always a bell, okay? And where it's centered on, according to your hypothesis, is 0.4. Okay, and our sample mean is, sorry, sample size is 50. So we already know that the sample variance, the variance, is 0.4 times 1 minus 0.4 over 50. Okay, this is this, but if you want the standard error, just take a square root, right? So this is the normal. Okay, this is the standard error of P, right? Or sometimes we play the SP, right? And the question would be, now we know is 0.5, right? And remember, our hypothesis said not equal to, right? That means that if this is too large or too small, you reject, right? And remember, it's two-tailed test. So this is alpha is 5%, so it's 0.025, right? These two area. Okay. And the question probably simply whether 0.5 is the 0.5 is here or here, right? Which is the case. The question is whether in the purple region or not. Okay. So because it's normal, so you can always convert to the z, and this become 0. And 0.5 is what? Okay. Remember, this is just p minus 0.4 over this capital guy, right? Okay. And this turned out to be 1.44. Okay. And the question is this area, okay? Is this area less than 0.025, right? Or this area multiplied by 2, which is p value, is it less than 5%? Okay. And to do so, look at this. This is area on the right. The Z table gives to the left. So 1 minus. So 1 minus norm as area to this number to area, this, right? The F table, right? It's 1.44, true. Okay. And you calculate that. Remember, not done yet. You multiply by 2. This is the p-value. Okay. And the p-value is 14%, as you would expect, because 1.44 is not 2 SE away. So 40% is too large. So you would not reject H null. You would keep H null because it's not enough, far away enough. Okay. Or on the other hand, you can also do the critical value method. Okay. Looking at both sides, where you got 2.5%, right? So you can just do this because they're symmetric. Okay, this is 0.025. Okay, and this number is norm standard inward 0.025 will end up negative 1.96. Okay, that means that the other side will be positive 1.96, and 1.44 is not within the region that beyond 1.96. So you will not reject. Okay, so that would clear the idea. Someone claimed the proportion is 40%. The data cannot tell, right? Even though it's 0.5. Okay, so what you do is you need more data, right? Although half of them is already not 40%, right? Not enough. You need more data, the bigger end, to reject that. Is that okay? Actually, you can notice when we do two-tail tests, the thing we calculate is very similar to interval estimator. Okay, indeed, actually you can show if you do 0.5 do an interval estimator, it will include 0.4. Okay, so that means that actually the two-tail test is closer to the interval estimator. If what you can do the estimation, if your interval estimator include the thing you hypothesize, then you can't reject. Okay, that same thing. But I'm not going to test this. This is slightly beyond the scope we want to cover, but that is something that you will notice if you are careful enough. Right? But I don't want to complicate your head already because this is something already very complicated. Okay? Okay, any question? Good. So now we've done one sample. This we're happy because you are asked to do anything, you're tasked to test the data, then you know how to do it. Okay, you know the variance, Z test. You don't know T test. Proportion, Z test. Okay, there's nothing very deep here, right? As I said, you may find this is not something you use very often. Other than you do audit, you do quality control. Okay, but later, as I said, when you do all the statistical analysis, this is something you want to check. Why? Because suppose later you see when we at the very last, at the very end of our course, we will do regression, where we are trying to have a model to build up to relate two variables, realign, and if we want this model to be useful, we want those parameters should not be zero, right? If zero, the model will be useless, right? So later we see we often do this to test the parameter are zero or not. Okay, and this is the underlying behind. We also are known for the same. We want to check if the model is useful, those parameters should not be zero. And this is the one sample test why we've studied. Otherwise, we should only start with the two sample tests. Okay, the one sample is very useful because we want to see, once we have the model, we want to see the model, the parameter we estimate is non-zero. If zero, the model is useless. Okay, we will be very clear at the end of our semester. But at the moment, this is already very useful already. But they're actually more useful when we try to see if the model has anything meaningful. So two samples. Okay. So here we cover all these 5 different tests. Okay. And these are very useful, although they're a little abstract, because after this class, of these 5 tests, we're going to study 2 different models, ANOVA and regression. Okay, and this is probably the last section that we go the most abstract level, because ANOVA and regression will be more concrete, and here we're a little bit more abstract. So as we said, we do 2 samples. Actually, we said it's just A/B testing, right? You can imagine you have a new app, an old app, right? You want to see whether the new app is doing better than old app. Okay, or you want to compare 2 different, I don't know, asset, right? You want to see whether SS1 have higher return than other assets, right? So that's a question. And you see there are 3 different cases. The first case is assumption of equal variance. The second case is without, okay? And of course, you will say this is more general than this one, so why bother the first one, okay? Later you will see, because if we know more, okay, our hypothesis testing will be more accurate. So this is always the case is, if you do the hypothesis testing with more general condition, you have the power of the test is not so good. If you know more, things will be getting better. Okay. So that's why we need to do both. And also, this is much easier to understand. This is more difficult to understand. So that's why we learn something simple first. Okay. And this is, you can imagine, I compare 2 different cases, right? Equal variance, maybe I want to compare 2 different shops, right? And I want to say, right, say they are both in Hong Kong Island. I want to see whether the 2 managers there, are they having same capability, right? Then you can assume equal variance, maybe Hong Kong Island the same, right? When you would want to compare with unequal variance is, say, for example, the data of one manager come from peak season, the data of other manager come from non-peak season, and you would imagine the variance is different. Okay. And here is the pair population. This is closest related to A/B test. This is before and after. The pair means that you have the same guy who subject to 2 different treatment. So this is exactly when you learn science. You only change one thing. You do observation. You see whether, say, the same plant, one plant has sunlight, the other have not. Then see sunlight is useful. Okay. Or the same subjects, use this app, how fast is reacting, and the new app there, how fast is reacting. So this is the pair. So this is closest to A/B test that you do in the real world. But of course, in many cases, you don't have the same observation on the same subjects. So that's why often you have to do this. Okay. But this is the most ideal A/B test, okay? Because the same guy, you observe him twice under different conditions. So he must be the individual difference is gone, because you cannot get the difference between the 2 different treatments. So this is basically the science, right? You only change one thing. And you compare mean, also you can compare proportion as well, right? You can compare, say, for example, I want to compare people who live in school or who don't live in school, right? Maybe people in school, they would study more than people who live at home, or I don't know, maybe the same or not, the proportion. The last one, we just go away from the mean. Now I go to variance. I want to compare variance of 2 different cases. Why I want to do that? That is, you compare variance is what? Application of variance in stock market is risk, a financial market. I want to compare 2 different financial instruments. Are they having the same risk or not? Is one stock more risky than others? Okay. And actually, this go back to here. The question. You would want to do the F test first, to see if they're different or not. If not, we can proceed to this one. Okay. But of course, in this class, I'm not asking you to do this, but this is the reason why I want to do this as well. Okay. I will not ask you to do this and decide which one to do, but this is something that you should know this closely related to this. Okay. But you will see this compare variance is very important in finance, right? You want to see two stock have same variance or not. Okay. You know they're risky or not. Once we know that, we can see whether if they're same variance, we're going to check whether they have same mean or not. Right? This is going to check this. Right? And once you know that, why I want to care about that? If I know the same variance, if one has higher return, right, then you invest that, right? So that is something very simple, right? This already gives you how do you pick a stock, right? Because in principle, in from data, one stock has higher return than others, right? But that is can happen anytime because historical reason. You want to see is actually big enough to avoid some sampling error. You don't want to make mistake because something realized, right? Because things can happen. So this would be something we'll cover after the break. Okay. So that would be something we talk is a quote for you. Okay. So as usual, I would like to invite you to fill in this. And since tomorrow will be our Halloween holiday, so as usual, I bring some candy for you. There's some Halloween style, non-Halloween style, and some salty stuff. So you can pick, mix and match. So we'll meet 2:32. So I just bring the Halloween and non-Halloween style. Trick or treat. Treat. Halloween, not Halloween. Oh. Halloween works. Non-Halloween. Yeah, they go not Halloween. Trick or treat. Trick or treat. Halloween. Inside. One straight. I teach you a lot of math straight. It's just the sweet.
Okay.
Yeah. Whatever. I don't know. When you drink coffee, usually you get it. Yeah, you can.
Yeah.
Maybe you want coffee. You have you are half. Any different? Getting this. By lunch. So dinner that I picked. I'll be there too. Okay. It's too bad. Yeah. Set up where you're head of. Okay, that's good. What are we read on? I don't know. I think I put it over.
Oh.
That's fine.
Yeah. People that ask you to ask.
No, it's at 9. If I get on the house. But every year they have 6 on the house. Different fee to try.
That's great.
They sell 60 per house, like 200 something. For free house.
Yeah, even for all those, I knew that who's going to stand there, who's going to shout, who's going to like, but still I was there. Like,
It's very funny this way. Long way.
I didn't know.
But if you go there, you can put a straight person. I'm really scared. They're not scared that much.
Oh, really?
Yeah, they provide it. Say, I want to be scared. You want to, don't want to stay. So they can put a thing, can do it for. They put a sticker, maybe fast sticker, or you take it to it. People can tell you whether you're scared or not. So, okay.
Like, it's what I was thinking about. Was like this things like the corridors.
Oh,
And then someone will drop the spider. She will drop the spiders. While they're coming.
what is it?
Yeah, because someone will jump on the wall. Oh yeah, I think there's just some jump on the wall. Where the screen.
That's nice.
Yeah, just for something.
Yes, pretty enough. Great.
Yeah.
We're like,
There's like a game where you like Like the card game, you lose them, they will like tell you.
I swear.
And
That's-
that they'll give you like eyeballs, it's like in the.
That's
That's fine.
yeah. Definitely. That's fun. Dress up.
Are you going to dress up?
Oh, my son. I passed the age.
Yeah.
Too old. to
Too
dress.
old.
But-
But sure.
But if I go to that iPhone, then I can.
Well, what is part of the that your last week?
Vampire.
Because you feel this.
Yeah.
I'm not pale. I'm not pale. Like, it's amazing.
It's fun.
Yeah.
That's what. In the school, because the school they have a.
Yes. My parents are open shop, like, yesterday they go, like, we just started to, like, that was the, oh, they,
Yeah.
oh, that's good. Are you sure there's like, just, there's days holiday, like, oh. Actually, that's not like.
Actually, pretty much you are one. But they.
But like in middle China, there's like the two people, they probably covered middle China.
Oh, I will try. Or study. But in terms of work quality, I think we have much less. So because people say they have a spring of holiday. They have fall holiday thing. They don't have.
Holiday. Like, working.
Yeah. In Europe, they have. Everyone has 1 month off. Pay off. Pay off. So everyone is like so fun. You can go to where Europe, right? So they July, nobody will get that. Everyone is gone. Everyone, except the tourist group, otherwise, the gold table and up on the table, June, July, or gone.
But we usually. Like. Where do you go?
Those people say dolphin, you, and possibly. America, or Asians. But most of the time, they have some,
Something in which. Some two POOR for them.
There's a lot of houses. Way that region. Of course, noise, somehow, but second. It's go for some, so I just get it.
They'll already have a hassle.
Yeah. But the pop-up is also, and some others.
Yeah.
Not mentioned at the top.
Yeah.
Not even.
That they get, quickly, the renters, which are, they die.
Yeah, that's a problem.
So.
Yeah, around Canadian. Yeah, then they go fine. Reasonable. And he said, about five.
Like, how much? Your squares.
800. I mean, that's square.
Yeah.
800 square. By at least 100 million.
And to look for this price. You could.
Yeah, one further, oh, doesn't really matter. No,
Yeah.
no, it's my wife who ordered this one. I just don't know. Someone have to not take it.
Like the, insurance for you.
I have to make sure zero risk. You should take all of this.
No, we're still on.
Oh, also the problems with cancer. It's how much time gets spent reading all these things and
Yeah. I know that they're like update. And everyone else is like, everyone, like 4 or 5 people like sit and then wait for like the update. Yeah.
figure out their system work.
What is that? That's it. And that's the very question. Like for students. Or you just like doing that.
Bad thing for everything go down. I've been excessive use my right. By predicting everything go down, so I'm going to do any process. I'm thinking everything's powerful. Oh, that's what that's what I thought. Now, we talk about the line. Also, all further profiles. There are not any values at all. So not there, I did. I got it.
Yeah.
I will not buy. I didn't go through it. And then go back. Even. Everywhere you go. Well,
So that's why it's so expensive right now. Another problem.
yes, but still very expensive. It was like more than 30% more.
So maybe like next year.
Even
Like it's like.
because other people go
By
back.
the time we graduate.
Yeah, other people go back. Right.
They're trying to sell their over again. If people will buy that.
Then will be go down because immigration of Shenzhen and Hong Kong. The two things, Hong Kong will go down, they go on to the people, yeah, salary, everything, yeah, okay. So our salary, our everything different. Now across the border, the demonstration, border, Shenzhen to go for $1 way more than it. The exchange price, Shenzhen border, was less than Hong Kong, high gold. People like they're dropping,
It's kind of new for fee.
yeah, you can
Go back to the beginning.
yes, go down a bit, but I don't go back to the now it's figuring stock price is facing up. So basically just tracking the Chinese one. So the now majority is stock is basically so there's no other very compound.
It's
I don't mean that.
yeah.
But when you go to Hong Kong, you have to invest in retirement, the pension. But I put all the pension in the office, nothing.
Oh.
Yeah. Because they're in healthcare, and if you can invest in, yeah, on Asia, a good early big program.
Wow.
You know, and it's also I do pretty good return. Yeah. 30%, the 40%. Okay.
Oh, okay.
Even negative.
It's better than negative.
Yeah.
Negative.
Because when I come back, the stock index very fast. £30,000, but it's if I buy Hong Kong, I feel connected. But because I invest elsewhere, so
Yeah,
it's still possible.
I feel like, if you look at the perspective, actually, like you're like having more money in your picture, but because of inflation, actually it's
Yeah, that's way.
Yeah.
I didn't depend on it's actually inflation.
Yeah.
How these things. Yeah, that's all. Not more expensive. No, you do be tech.
Always be.
I don't think there's any chance that they would have. I kind of see between 10 years. Really. Anything I don't know. I can't see the more than 10 years. I can't see the meter. Unless the one you do. There's a water specific. Otherwise. Well, only if there was more China will be like otherwise.
Yeah.
Then we West mean that.
Right.
So let's see. How are you doing? Yep, I hope you have more treat from Halloween. You learned the math trick from this class. So I think you got enough tricks, so you should get more treat in the Halloween period. Yes, I did actually. I take a lot of rest. I mean, while I'm doing stuff at home, and my kids are actually doing a lot of exercise because they have exam next week. So I at home, everyone's doing their own stuff. So really enjoy. And my disease got much better, so we recover much faster. So hopefully after the weekend next week, when I saw you, then I fully recover. You don't hear my coughing. Yeah. Oh, good. So last sample C test. Yep. You want to compare the variance and also want to compare the mean as well. Yeah, one key point. Yeah, that's good. The speed is okay. I'm glad that overall is fine. 4. Most of you still find easy to follow, which I'm very glad. Oh, luckily, this time we have something. At least 2 people say, "No, now we're happy after the holiday." Hopefully, with more tricks, then you have more better, and like this. Okay. This morning I have PhD classes. Turn out that all of them are here. All of them here. Know this, and know this. That's what PhD people looks like. But any jokes? Yes, I think statistics is very useful investment because investment is about future, right? Look at future, you have to look at how can you look at future, look at the past and past data, right? Statistics, right? To quantify the future using the past data, use probability. So that's why this class is required for everyone in business school, right? Because you need to know the future. I went there already. So go to the Ocean Park, which is pretty fun. I recommend you to go to them, especially the one on the top of the mountain. The free one is very nice. The bottom one is also okay. Yeah. I still remember one of the action in the Ocean Park. Oh, I remember. Trust your DNA. That is one of them. It's like a squad game. But anyway, I should not say more because you left your fun if you go there. I can't see that easily. Is it something I have to check? Let's see. What's that?
走啦，係咪？有啲人開心咧，
雪櫃冷笑話。
嗱，啲人咧唔開心啦就會飲酒啦，係咪？有啲人開心咧就會飲糖水啦。如果想表達愛意嘅話，應該飲咩咧？
飲咩咧？
好你。
So, for those who don't know, it's just a joke. And he said, if you, let me, I don't know what he said. We say when you're happy, then you, I forgot. I said, some people not happy will drink alcohol. And some people happy, they will drink sweet desserts. And they said, if you want to send out your message of love, what we would do? And they said they should drink pu'er. Pu'er is a type of tea. You go to every Chinese restaurant. You ask for and that is the same sound as typing. So that's the fun they want to play around with. But it's very, very holy. But anyway. So we have good fans for the joke. I think we haven't had this kind of joke for a very long time. Because they used to send me all kinds of crazy jokes put there. But now this cohort doesn't seem to like to share this kind of nonsense jokes, but that's okay. So let's look at this, okay? Let's now look at the model we have, right? So we will start to have two population. They are both normal, okay? And observation, one has mean mu1 and sigma. That means it's the following. We have this 1, mu1, sigma 1 square. We have this x1, x2, mu2, sigma 2 square. So that is what it means. And every observation will be x11 will be first observation from 1, second observation from 1, n1 observation 1. And same as first observation from 2, second observation from 2, and n2 observation from 2. Okay. So basically you draw from both pair. Okay. And the independent, which means that any information from one population can't tell the others, right? Which means that you know mu1 cannot tell you from mu2. You know sigma 1 square doesn't tell you anything about this. So they're independent. Okay, independent. Two bell curve. Okay. And that means the sample mean will be average of what you see from 1 divided by how many 1 you have. right? Sample of 2 will be average of 2, right? And if you random sample, the sample mean of 1 equal to population mean of 1. Sample mean of 2 will be equal to population mean of 2. And variance of 1 will be variance of 1 over n1, and this is the same, right? So nothing new here. Sorry. And same as the sample variance, okay, will be n-1 minus 1 and n2 minus 1. And they're all unbiased, okay? So there's nothing new there, okay? Nothing new information from here, okay? And as I said, we assume that bell curve, okay? So this means that the sample mean follow the bell curve as well, okay? So once we know that, we are ready to do hypothesis testing or A/B test, as we said. So that's a very simple question. So we have some maybe a sample mean come from one city, right? And sample mean come from that city, right? Maybe you want to say the difference between two cities, right? Or maybe this is store number 1, store number 2. We want to see whether the difference of the sample mean will follow this, okay? And then want to see whether this is equal to 0 or not, or equal to some number or not, okay? So that's a question where we want to compare two different mean, right? Or you can imagine this is stock number 1, stock number 2. You want to compare two different stocks, but they have same return or not, okay? So that will be the idea. Is that clear? So I have two different set. So the question would be, store A better than store B, product A better than product B, or vaccine A better than vaccine B, right? So that will be the question. Okay. So we can solve if we assume that they have the same variance. Okay. We can estimate this sigma by this formula. Okay. It's a weighted average of the first sample variance over the other sample variance. We can prove this formula, but this is not something complicated to understand because this is the weighted mean. This is a ratio. You take the numerator is n1 over minus 1. The other is n2 minus 2, right? So that means that actually which one has larger sample will have higher weight, right? Because if sample larger, then it's more accurate, right? So it's basically weighted mean over these two, okay? And the proof is on the second page, which I don't think I have time to prove this is good proof, but this is the proof behind why this is a good one, okay? I'm not going to go over the proof, but this is the formula, okay? And you can see this is not something terrible, but because you can bring your cheat sheet there, right? So basically just use it. And I'm not going to show you the proof because I guess no one interested in the proof anyway, right? I can actually just freeline the proof, but I see no one interested in it anyway because that is standard. So what we want to know is, suppose they're same variance, okay? You can't, why they have same variance? Later you do the F test, you check their same variance, okay? Or from historical data, you can imagine Shenzhen and Hong Kong maybe have same variance, or different store have same variance, okay? If you don't, then you add this formula. But if the same variance, you want to check whether they're the same or not. A/B testing, right? You can imagine have a new system and old system, right? You look at aggregate data, whether it's 0 or not. Okay. And you will see, right, because of this, right? You take the difference, minus 0 means 0, right? And over this square of this guy, which we place by estimate, is t. Okay. Let me draw a picture to show you what I'm doing. So you have population 1, by some number here, right? And this will follow a bell curve, as we mentioned, which have mu1, right? And we assume this is going to be sigma 1 squared, right? And you collect the sample mean, it is still here, but much thinner, right? And you also have another population x2, some observation here, okay? And we also claim this is a bell curve, have mean mu1, sigma 2 squared, okay? And you collect the sample mean is also here, okay? Okay, and we know that assume this is equal to sigma. Okay, now since I care about the difference, right, I hypothesize this, right? That means that the difference, the bell curve, will mean 0, right? And the variance will be simply add together. Remember, right? Bell curve, difference, the variance is to add together. Remember the slide we mentioned, right? Will be this. This will be variance of this, but since they use sigma, so just sigma square over n1 plus sigma square over n2. Okay, so this is the idea. Okay, so that is what we see, right? So we can do Z test if no sigma, but we just make our life easier. We skip the Z test, we do T test, right? The T test will be asking this, right? Alpha for 2, alpha for 2, right? And we do the T test, right? It's a T, okay? And as I said, the only difference T is degree of freedom. Which table you're checking? This table you check will be N1 plus N2 minus 2. Just to remember, there's nothing, we can prove it, but we don't want to do that. But just to remember, this is 0 to this guy, right? And what is the SE of this guy, right? We want the SE of this guy, right? The standard error is coming from square root of SP square over N1 plus SP square over N2, right? SP is estimating sigma, right? What's SP? If you still remember the formula, which I don't need to remember, will be N1 minus 1, N2 minus 1, S1 square, N2 minus 1, because this is just weighted average, right? So that's the idea. Okay. You basically look at the data where you are, right? And you convert this distance divided by this SE will give you where you are, right? And you check. So that is the idea behind this. Okay, the only new item compared to the single one is this guy, and let me use black color, right? Will be only this guy, the new thing, and this guy's a new thing, right? Otherwise, everything's old, as old as the previous one, right? Because the difference of the sample mean is also a normal, right? So nothing is it, although it's a two sample test, at the end it's still one sample, right? The difference is still a bell curve, right? We're checking the bell curve is between 0 or not. Okay, don't worry. Let's go to example. I'll do it and then you'll see. As I said, it's rather boring because we keep doing the same thing, right? And one thing I want to say further is we can do the interval estimator, right? Will be just, as we said, you just multiply the denominator by the critical value, right? We just said before, will be our interval estimator. So this is the formula. Okay. Let me work out this example carefully and slowly so that you understand this, because this, once you know this, you know what's going on. Okay? There are a lot of stuff here, so I have to be a little bit more careful. Okay? So let me go to the example. So I have two populations. They follow normal. Okay? And we know that they have the same variance. Why? F-test later. But assume this is true. So we have first sample size 50. Sample means 40. It's 4. Okay? And the other one is 40, 42, and 3. Okay? And this is one to test. Okay? So let us write down this. Okay? Write down here how we do this problem. Okay? First, we start with our hypothesis, which is mu1 equal to mu2. And our alternative is mu1 not equal to mu2. Okay, this is our question. And let's look at the data we have is sample 1, we have x1 bar is 40, s1 is 4, and n1 is 50. Okay. And x2 bar is 42, s2 is 3, and n2 is 40. Okay. So just to remind you, what we are seeing here is x bar 1 bell curve with mean, I don't know, it's mu1. Okay. And this is sigma 1 square over n1. N1 is 50. We know that happened. And x2 bar is somewhere mu2. Okay. And mu2 square over 50. Okay. And under the null, we set that same. Okay. Some number mu. Okay. Okay. So what does that mean? It means that under the null, this x1 minus x2 should center at 0, right? Because they have same mean. Okay. And it also a bell curve, because remember, bell minus bell is still a bell. Okay. And the location will be just different between that, and the variance is mu square over 50 plus sigma square 2 over 40. Oh, sorry, that's a mistake here. It's 40. Okay. Make it more careful writing. Okay. So that is the answer. Okay. And what we're going to do, right? Suppose we know sigma 1, sigma 2, then it's easy, right? Because that means that I just need to know two-tailed test. I want alpha over 2, right? If it is the data is belong to the green region, then we're done, right? And the data tell us that it's -2 because this is 40, this is 42. So what we have is -2 here. I don't know it's here or here, right? So there's a question, right? If -2 is in the green region, then we reject. Otherwise, not. Okay. So again, we don't know the sigma, right? So we replace this by S, but since we assume this assumption, right? We know this. So we assume this is the same. We can guess this by what we call SP square. And SP square is simply, if you look at the formula, is N1 minus 1 over N1 minus 1 plus N2 minus 1 S1 square plus N2 minus 1. You have same. So this is the formula. And look at the slides. The answer of this is 12, right? It's between 16 and 9, right? And it's more closer to 16 because we have larger sample than X, right? So it's 12.2. Okay. And N1 is here, N2 is here, S1 is here, S2 is here. So just plug in all the number. Okay. Right? So once we know this, then we're done, right? Because this I can convert to T N1 plus N2 minus 2, right? So this is actually T 98? No, 88. Because 550 plus 40 minus 2, T 88, right? And this is 0. And what is 2 here? -2, right? It's -2 over the square of this guy, right? So this is what? -2 over square root of, we place, this is 12.28, right? 12.89 over 40, 50, right? Plus 12.89 over 40. Okay. So this is the number. And which is here in this slide, which is -2.6. Okay. Which here is -2.6. Okay. So the question would be, there are 2 ways to do it. You check this number, the area, multiply by 2, is it less than 5%, right? So what we're going to do is T, this, -2.6, 88, true. And remember, we are doing two-sided test. What about you? And you compare this to the alpha, which is 5%. And if this is less than 5%, you reject. If this is more than 5%, you don't reject. So that is the idea behind. Okay, I stop a little bit because I think this is complicated. I don't want to rush through, but hopefully, as I said, there's nothing new, but the only new thing is compared to the old cases, is a bell curve. The only new thing is TATA and how you calculate the standard error of the mean, right? Which you have to, cannot just plug in S1, S2, right? You calculate this pooled sample and plug in there. So there's only trick goes on. Is that okay? So lastly, I want to talk about two things, is the p-value and interval, right? I guess I will stop after this slide because I know I overrun a lot of time. So I let you go earlier today because you will celebrate your Halloween earlier. So if you want to do the p-value, critical value, we'll be asking what happened if this is 2.5%, right? 0.025. Okay. So that means that the critical value will be T dot inverse 0.025. Okay. 88. Okay. This will give you the negative side, right? If you want the positive number, that will be 0.975, 88. Okay. And this gives you the critical value, right? And if this is the value that more than 2.6 or less than 2.6, we decide whether you reject or not. So this critical value method. Last but not least will be the idea of confidence interval, right? If you remember, hope you still remember, how you do the one sample test, right? One sample thing, this, right? X bar sigma square over n, and this mu, right? And how we do the interval is X bar plus minus Tn1 minus alpha over 2 S over root n, right? Or X bar plus minus Z alpha over 2 sigma over root n, right? So same goes on here. It just now the mean is the difference. So this is just x1 bar over x2 bar, which is original case, plus minus, this is t, n1 plus n2 minus 2 is 88 alpha over 2, which is a critical value, right? So this is always a critical value. And this guy is just the pooled variance over 1 over n1 plus 1 over n2, right? So this is the denominator, right? Just if you remember, weigh carefully, okay? This guy is just our critical value. Same thing. And this guy is from our denominator. So that's why I say the two-tailed test is exactly the same in our case of our interval estimator, right? And in general like this, but there's some cases not the same, okay? But in this particular case, the same thing. Okay? So In the next class, we'll talk about the case where you don't have this, you have a formula, okay? And you have more complicated degree of freedom, okay? Which I will cover next week. As I said, I offer overtime, so I give you 5 minutes earlier so that you can celebrate your Halloween earlier. So I see you next week. Enjoy. If you need more candy or sweets or salty, come here and get more. Enjoy the holiday. I'll see you in November.